This is one of the harder questions from the homework. The first thing you need to do is make sure that any additional information that's in the question is added to your diagram. For instance, the question specifies that the distance from A to T is 2.1 meters along the track. You can't make any headway with part 1 of the question until you've marked this on. So the first thing we have to do is find out how much work is done by the car against friction as it moves from its starting position at O to T. Well, work done is simply force times distance. You've been told that the frictional force is 0.06 mg, and we have to multiply this by the distance along the track. Well, if you do that calculation, you get 0.186 mg joules. That is the work done against friction between the point O and the point T. So that's part 1. Second part asks you to find the kinetic energy at this point here. Well, the kinetic energy at that point is going to be equal to the gravitational potential energy at that point minus the gravitational potential energy at that point minus the extra work done against friction on the way. So that is going to be initial GPE minus 0.186 mg minus, well, we've got a height of 0.75 there, so 0.75 mg. That is the kinetic energy. The only one we actually have to work out is the initial GPE. And we can do that by using GPE equals mgh, which equals mg. Now, that height there consists of 0.3 meters plus 1 times the sine of that angle, sine 60 degrees. If you work that lot out, you get 1.166 mg. Therefore, the kinetic energy is simply going to be 1.166 mg minus 0.186 mg minus 0.75 mg. And if you do that calculation, you will get the answer 0.230 mg as required. This is an energy value, so I guess we should write J for joules. And that is the end of part 2 of the question. Part 3 of the question requires us to show that the car remains on the track at this point here. For that, we need to show that the normal reaction of the track on the car is greater than 0. The normal reaction of the track on the car is equal to the force required to deliver the circular motion we have, which is mv squared over r, minus the weight of the car. And we can immediately rewrite mv squared as twice the kinetic energy. And we know what the kinetic energy of the car at point T is, so we can rewrite the equation with that figure in. So now all we need to do is convince ourselves that that value there is greater than 0. Okay, let's take out a common factor of mg, and it's quite obvious that 0.46 over 0.3 is greater than 1, therefore that is greater than 0. Therefore, car stays on the track. Now it gets a little bit trickier. We are told the car stops here, at point C, and have been asked to find what is this distance, BC. Well, we're going to start by calling this distance x, and then we're going to look back at the question and notice that this track is described as symmetrical. Therefore, the distance from T to B is 2.1 meters. So we now know that the entire distance from T to C is 2.1 plus x meters. What we need to think about now is energy. We know how much energy the car has at T. We know that between T and C, it will lose some energy to friction and some to gravitational potential energy. Let's work out those two different parts separately. First of all, energy lost to friction is simply going to be given by the distance, 2.1 plus x, times the frictional force, which is 0.06 mg. We used that back in part 1. Next thing we need to work out is the energy lost to GPE. And that is going to be mg times the gain in height, which is the height at C minus 0.75. Okay, well we can work out the height at C by doing 0.3 meters plus x sine 60 degrees. Therefore, the total energy lost between T and C is given by energy lost to friction plus energy lost to gravitational potential energy. But we know it comes to a standstill at C, therefore that energy loss must correspond to the total energy it had at T, which is simply 0.230 mg joules. Oh look, we can cancel out all the mg's, and as you can see I'm left with a very messy looking equation, but it is just a bit of algebra. So I'm going to tidy up over here. I'm going to collect up my x's on the left, so I get 0.06x and x sine 60 degrees. If I take all my values over onto the right, I get this lot. I do a quick sum and find that that lot comes to 0.554. Meanwhile, on the left, I know that sine 60 is root 3 over 2. I can factorize that and end up with a decimal times x, divide my 0.554 through by that value, and I get a number for x. The value is 0.598 meters. Hurrah! Finally, the question asks, given that the car makes it to this point, will it make it all the way back around the loop? Well, to do that, once again, we have to look at energy. And we're going to start off by finding out how much energy it's got at this point. It's got no kinetic energy. It's stopped. Therefore, all it has is GPE. And the GPE it has is going to be mg times the height, which is simply 0.3 plus 0.598 sine 60 degrees. Well, you can shove that lot into your calculator and come to the conclusion that that comes out as 0.817 mg. So that's the gravitational potential energy it's got there. Now, between here and here, it is going to lose a certain amount of energy due to friction. We've done this a couple of times already. It's got that distance there, x plus 2.1 meters. So lost to friction is simply 2.1 plus 0.598 times 0.06 mg. That's the energy that goes to friction. If I work that lot out, I get 0.16188 mg. So by the time it gets to here, all the energy it has left is that minus that. 0.817 minus 0.16188. The residual energy left, once it's lost that energy due to friction, is about 0.65 something something something. Hang on. 0.65 mg isn't even the 0.75 mg it needs to get to this height. Never mind whether or not it's got enough energy to actually stick to the track, it can't even make it to this height. So the answer to the final part of the question is no. There is not enough energy left in the system to take it back to the top of the loop. And that's the end of that quite challenging question.